And now the next reaction of carbonyl compounds on our list is their reaction with alkali. We shall treat two of such reactions. First, we'll look at the reaction of carbonyl compounds with dilute alkali. That reaction we refer to it as Aldol condensation. Then we're going to look at the reaction of carbonyl compounds with concentrated alkali. And that reaction, we call it the Cannizzaro reaction. Let us start with our Aldol condensation, which of course is the reaction of carbonyl compounds with dilute alkali. The alkali we use in that case could either be sodium hydroxide or potassium hydroxide. There are key things you should know about this reaction. One of them is the fact that the carbonyl compounds undergoing this reaction with dilute alkali must have an alpha hydrogen. Take note, a very important point, which means if the carbonyl compound does not possess alpha hydrogen, then it cannot undergo this reaction called Aldol condensation. I hope that is clear, right? Now, let us proceed to explain what happens in Aldol condensation reaction. During Aldol condensation, the carbonyl compounds undergo self-condensation in the presence of the dilute alkali, which I stated could either be sodium hydroxide or potassium hydroxide. Now, if it is an alkanal that undergoes this Aldol condensation, the product you're going to get, we call it the aldol. Aldols are beta hydroxyl alkanal. So you take note of that. If the carbonyl compound is an alkanal undergoing self-condensation in the presence of a dilute alkali, then you get what we call aldols. And aldols are beta hydroxyl alkanal. Now, if it is an alkanone, that is the carbonyl compound undergoing this Aldol condensation, you are going to get what we call ketose. Ketose. And what are ketose? Ketose are simply beta hydroxyl alkanones. Take note of these terms, okay? Now, when we obtain our aldols and ketose, depending on whether you use alkanals or alkanones, respectively, in this Aldol condensation, the aldols or ketones that you obtain, you can decide to heat them. When you heat them, you are going to get an unsaturated compound. Now, if you heat an aldol, it will produce alpha-beta unsaturated alkanal. Alpha-beta unsaturated alkanal is simply an alkanal that has an unsaturated bond, specifically double bond, between the alpha and the beta carbon. I've explained this concept of alpha and beta carbons in our previous classes, okay? So when you heat an aldol, you have a double bond between the alpha and beta carbon of the parent chain. That compound is called alpha-beta unsaturated alkanal. And there is a special name we give to them, the enals. Enals. In our IUPAC nomenclature of carbonyl compounds, alkanal, we meet something like that, the enal groups. Okay, what if it is ketone that you heated? If you heat a ketone, you will get alpha-beta unsaturated alkanone. And remember, our alpha-beta unsaturated alkanone is simply an alkanone that has a double bond between the alpha and the beta carbon. This alpha-beta unsaturated alkanones has this special name given to them called the enones. Is that okay? Called the what? The enones. So this is the idea. Aldols give us enals when you heat them. And then ketose gives us what? Enones when you heat the ketose. Now follow along as I show the chemical reaction of carbonyl compounds in this Aldol condensation process. Here on the board, I have this alkanal. This alkanal is ethanol. There are two molecules of it. Now you notice that this CHO, this C is the carbon of the functional group. Attached to this carbon, we have this CH3. This carbon is known as the alpha carbon. And you see clearly that on it, we have hydrogens, 3 of them. The hydrogens are known as alpha hydrogen. Now remember I told you that in Aldol condensation, the carbonyl compounds, whether alkanal or alkanone, should have what? Alpha hydrogen. Therefore, this compound, ethanol, can undergo Aldol condensation. Let us see what happens in the reaction process. I'm going to demonstrate that, and so you watch what I'm going to do here to help you understand how this self-condensation takes place. Now we have 2 molecules of ethanol. So I'm going to write CH3, and then we have CHO plus another CH3. Permit me to expand this functional group part. Plus another CH3, and then C double bond to oxygen H. Now this is what happens. One of these compounds, alright, will release one alpha hydrogen. Let us assume that we decide that, okay, this should release one alpha hydrogen. If this releases one alpha hydrogen, so you're going to get hydrogen positive, and then this becomes CH2, C, double bond to oxygen, and then single bond to hydrogen. Now you see clearly that the number of hydrogen on this carbon is no longer complete. Therefore, this is an ion. This is actually a carbanion. Is that okay? Now, this hydrogen ion and this carbanion will now attack this second carbonyl compound, this ethanol. I hope you're following, right? Now, when they attack, see, what happens there is something you've already learned. You remember when we treated nucleophilic addition reaction, I told you that a nucleophile attacks the carbon of the functional group, breaking the double bond holding the oxygen into 2 single bonds, right? Then hydrogen will attach itself to the oxygen, giving you the OH. Whereas the nucleophile will now attach itself to the second single bond. We encountered such reaction when we treated the nucleophilic addition reaction of carbonyl compounds with hydrogen cyanide. We also saw that when we treated the reaction with sodium hydrogen triosulfate 4, and of course when we treated the reaction of carbonyl compounds with ammonia. So exactly what happens there will now happen here. Is that okay? So let us watch. As these 2 species attack this ethanol here, then we're going to get CH3, which is this compound, untouched. This alkyl, untouched. Linked to this carbon, these 2 species will now attack this carbon of the functional group, breaking this double bond holding this oxygen to 2 single bonds. Now this is the oxygen, the follow-come oxygen, negative. This is the follow-come hydrogen. Then this is an empty bond. The empty bond will now take this carbanion, which is CH2, C, double bond to oxygen, and single bond to hydrogen. This hydrogen will now attach itself to this oxygen, giving us something like this. This is the compound we call the aldol. This is the compound we call what? Aldol. This is aldol because we obtained it from alkanal. This is ethanol. I said that already. And did you notice something in this aldol? This OH is on the beta carbon. Remember, this is the carbon of the functional group in the product formed. This first carbon attached to it is our alpha carbon. The second carbon to the carbon of the functional group is called our beta carbon. And of course, this is our gamma carbon. I've explained all these concepts in our previous classes. Now, our OH here is formed on the beta carbon. And what does that tell us? Aldols are simply beta hydroxyl alkanal. I take that again. Aldols are simply what? Beta hydroxyl alkanal. And of course, that is what is going to form there as products. I've shown you the clear reaction, what leads to that. If I had written the product here directly, it may not make sense to you clearly. Okay? But I think with this mechanism shown to you here, this step-by-step reaction, it helps you to understand how this product forms. So the self-condensation of this ethanol in the presence of this dilute sodium hydroxide is going to give us this compound. CH3, then we have C, OH, we have H here, and CH2, C, HO. Remember, this carbon that is bonded to this oxygen with a double bond and singly bonded to this hydrogen is the same as CHO. This is our aldol. Aldol. And in brackets, I'm going to write beta hydroxyl alkanal. Correct. Now when you hit this compound, the aldol, you are going to get alpha beta unsaturated alkanal. And that I'm going to demonstrate as you're going to see. Let us hit that compound form there. The compound form is CH3. We have this CH2 and then CHO. If I hit this, what is going to happen? Watch. We said that the compound that is going to be formed is alpha beta unsaturated alkanal. This is our alpha carbon. This is our beta carbon. You know, when you are hitting, it's as if you are pulling out water molecule from it. Of course, that's what you're doing, dehydration. Following set-step rule, this OH will be removed. So in fact, let me star it here, let me asterisk it. The OH will be removed, and then hydrogen will be removed from this alpha carbon. Minus one hydrogen. Now take note, according to set-step rule, if I'm removing OH from this carbon, then the hydrogen will be removed from the adjacent carbon, which has the lowest number of hydrogen. Adjacent carbon means the neighboring carbon to this one. This carbon, I'm removing OH from it. Now, there are two carbons surrounding it, CH3 and CH2. Set-step rule said you should remove hydrogen from the CH2, the one that has less number of hydrogen atoms. And once that is done, the product is going to give us CH3, then CH. We have a double bond. Remember, you removed an atom here, you also removed one from here. Therefore, you introduce double bond between two of them. And this is CH, CHO. This is our alpha beta unsaturated alkanal. I'm going to indicate it. This alpha beta unsaturated alkanal is known as our enal. Alright? Enal. Now we shall also look at a reaction whereby an alkanone undergoes Aldol condensation. We are done with using an example of alkanal. And now we are going to look at the Aldol condensation of an alkanone. This alkanone I have here is propanone. Alright, this is the carbon of the functional group. To its left and right, you have CH3, CH3, clearly telling us that there is an alpha carbon. And you notice, okay, let me focus on this as the alpha carbon. You could take this as the alpha carbon instead. The choice is yours. But if you had more carbons on one of the other side, either here or here, that part is where you now follow as your alpha carbon, beta carbon, gamma carbon. Is that okay? But in this case, any one of them can be taken as your alpha carbon. Now you notice that each of these carbon, okay, focusing on this, there are 3 hydrogens there. So we can say that propanone has what? Alpha hydrogens. Propanone has alpha hydrogens. So during the Aldol condensation, what is going to happen? I will demonstrate that here quickly. 2 molecules of propanone, so that's going to give us CH3, C double bond, and then CH3 reacting, self-condensation with another propanone compound. So we have this. And so what is going to happen? Let me pick this to be the one which is going to release the alpha hydrogen. So if it releases one alpha hydrogen, you're going to have this H positive, and then of course this will become CH2, CH2 negative, C double bond to oxygen, and then CH3. This is a carbon ion, and this is our hydrogen ion. These two will attack this carbon of the functional group. Similar thing that happens in the Aldol condensation using alkanal will also apply here. So we go. When they attack this compound, we are going to get CH3, then this C. What is going to happen to this double bond? It will be broken into 2 single bonds. You can see that. Now we have our follow oxygen there. And this CH3, please permit me to write it here. So I'm bringing it down here so that the second double bond will be here. Is that okay? So we are saying that this double bond is broken into 2. One up, then I fix the other one this direction because this CH3 I've decided to write it downward. Just a rearrangement. There is no error there. Is that okay? Now you see clearly that the alpha carbon of one of these alkanone, just like we saw in that of alkanal, the alpha carbon attacks and attaches itself to the carbon of the functional group of the second carbonyl compound, undergoing this self-condensation reaction, the Aldol condensation we are treating here. Watch. This alpha carbon, that's what split to give us hydrogen, and this CH2 negative, the carbanion. So it is the alpha carbon that will now attach itself, to this carbon of the functional group of the second carbonyl compound. So watch that. Let me use blue marker to show that now. This hydrogen will attach itself to this oxygen, giving us the hydroxyl. Then this carbanion, with this carbon of, that's the alpha carbon, will now attach this way, CH2. And then of course we have C, double bond to oxygen, and CH3. Now this is how the product is formed. And this compound is what we call the ketone. If you see clearly, this carbon is the carbon of the functional group. Now in this form that this compound is, talking about our alpha carbon, we are going to go to the left. Why? Because we have more carbon atoms on the left hand side than we have on the right hand side. So this is our carbon of the functional group, this is the alpha carbon, this is the beta carbon, this is the gamma carbon. Is that okay? Now this ketone, you see that on its beta carbon, that is where we have our OH, which means that ketones are actually beta hydroxyl alkanone. Remember, this is an alkanone. Alright, I think I can bring it here now. You've seen what happens to form the product. So this undergoes Aldol condensation. In the self-condensation process, we are going to get a product as CH3. Let me write it, just focusing on this now. I've shown you how it's been done. So we have CH3 coming to this. This is the carbon of the functional group. That is where the reaction will take place. So this oxygen, its double bond will be broken to single bond. Let me fix one here. Let me fix another one here. This CH3, please permit me to bring it down this way. Just like I explained there. Is that okay? So we now have single bond from the double bond holding this oxygen. Now let me fix this oxygen up this way. It's a follow come oxygen from one of the alkanone. Now what is going to happen? Remember, we now have the second CH3, CO, CH3. That second CH3, CO, CH3, one of the alpha carbon will release its alpha hydrogen. That alpha hydrogen will attach itself here. Let me use black marker to show it. Is that okay? To attach itself here. And then, remember, you're going to get a carbanion, which is now CH2 linked to CO and then CH3. So that goes this way. CH2, then C, double bond to oxygen, and our CH3. So you see, I can actually write a product even without going through this step-by-step analysis. But let's have to do this so that you would see it clearly yourself and understand how the product forms. So this compound is what we call our ketone. And this ketone is beta hydroxyl alkanone. Alright, we are going to proceed, Having obtained this ketone, what happens when you heat the ketone? So that I'm going to show here. We have the ketone here, and that compound is CH3, C, then OH. We have our CH3 here, then CH2, C, double bond to oxygen, and then CH3. Let us hit this and see what we're going to get as our product. Remember, following Setzer rule, we have our OH here, which is going to be removed. The heating process is a dehydration reaction, so you are pulling out water molecule. Now, if I remove OH from here, following Setzer rule, you're going to remove hydrogen from its adjacent carbon that has the lower number of hydrogen, that has the smallest number of hydrogen. And if you see this is CH2, this is CH3. So we remove hydrogen from this CH2 following Setzer rule, minus 1 hydrogen. And this carbon is our alpha carbon. So essentially what we did here was to remove 1 hydrogen from the alpha carbon, and then we removed OH from the beta carbon. What is now going to be the product? CH3, C. We have our CH3 attachment here. Then of course there's going to be a double bond between this beta carbon and this alpha carbon. We removed 1 hydrogen from here, so this becomes CH. And then we have our C, a double bond, and then CH3. This compound is what we call the enone. Let me indicate it, enone. And of course, this enone is alpha beta unsaturated alkanone. The enone is what? Alpha beta unsaturated alkanone, because the double bond is between the alpha carbon and the beta carbon. But what's the name of this compound specifically in terms of IUPAC nomenclature? Let's find out. There are 5 carbon atoms in the parent chain. Now on the 4th carbon atom we have the methyl attachment here. Then on the 3rd carbon atom, observe that we have our double bond. On the 2nd carbon atom we have the main functional group. So this compound is 4-methyl pent 3-ene 2-one. Once again, 4-methyl pent 3-ene 2-one. That's the IUPAC nomenclature of this enone. And like we said, this enone is alpha beta unsaturated alkanone. This is much about the Aldol condensation. Please take note that through this Aldol condensation, once you get the enal from aldol, alkanal, or you get the enone from ketone, when you hit ketone, that's from alkanone. If you react that, or you carry out reduction reaction, reduction reaction is introducing hydrogen. Usually you obtain saturated alkanol. We use this method to prepare compounds like butanol. That is, if I reduce this enone here, okay, by introducing hydrogen, the hydrogen will break this double bond to single bonds, and then attach itself here. And then one hydrogen will attach to this OH, and another one here. So just like introducing 4 hydrogen atoms, this will convert to an alkanol. I hope that makes sense. You can put that down, right? Reduction of enones and enals will give us saturated alkanol. And like I said, we use this method to obtain something like butanol. You can also use it to obtain 2-ethyl hexanol. Meanwhile, before we move on to Cannizzaro's reaction, I've got this question to ask you. Please take a look at this compound we have here, right? This is just a general form of some compounds, apart from this one, which is methanol. This is methanol. The other ones are general form of compounds. For example, like this could be something like this. C6H5, then CHO, that's phenylmethanol, alright? And then you could also have this, you can expand this and find out the compound it is. It's also an alkanal family anyway. But you notice that after this, you have this carbon, there's the carbon of the functional group, you have this carbon. On this carbon, there are 3 alkenes attached to it. And then so on. Here you have this aryl group, phenyl, C6H5, CO, then C6H5, and then this one. This is an aryl, a phenyl group, and then this is an alkyl group. This is the carbon of the functional group. So my question is, can any one of them undergo Aldol condensation? Think about this. If you identify the carbon of the functional group, and then you locate, maybe you're talking about your alpha carbon, would you see anything like alpha hydrogen? Or would you actually even see an alpha carbon in there? That will help you to know whether they undergo Aldol condensation or not. Take a look at this. This is methanol. This is the carbon of the functional group. Do you see clearly there is nothing like alpha carbon? So we can't even think of alpha hydrogen. Therefore, what do you have to say about methanol? Does it undergo Aldol condensation? No. What about this? Okay, this is phenyl methanol. Is there any alpha carbon? There is no alpha carbon. This is not an alpha carbon. This is a group on its own, phenyl. Is that okay? So it does not undergo Aldol condensation. If you move on to this is the carbon of the functional group. Now you have this as our alpha carbon. On this alpha carbon, there are 3 alkyl groups attached to it. Permit me to expand this compound for you, please. This is just something like C, CHO, and then on this you have CH3, CH3, and then CH3. Good. Now you notice that this is our alpha carbon. On this alpha carbon, do you have any hydrogen directly attached to it? No. What you have there are alkyl groups, 3 of them, just like you have this RE3. 3 alkyl groups, no alpha hydrogen. Therefore, it cannot undergo Aldol condensation. Remember, for Aldol condensation to be undergone by a given compound, for a carbonyl compound to undergo Aldol condensation, there must be what? An alpha hydrogen. It is now time we're going to consider the next reaction with alkali, this time around concentrated alkali, the Cannizzaro reaction. And now, the Cannizzaro reaction. This is the second form of reaction of carbonyl compounds with concentrated alkali. We call that reaction Cannizzaro reaction. Now, for this reaction to take place, the carbonyl compound must not contain alpha hydrogen. Please, very important. Because when we treated Aldol condensation, I stated that a carbonyl compound is expected to have what? Alpha hydrogen. But in the case of Cannizzaro reaction, the carbonyl compound should not contain any alpha hydrogen. Now, in the process, the carbonyl compound undergoes self-oxidation and reduction in the presence of a concentrated alkali, which could either be concentrated sodium hydroxide or concentrated potassium hydroxide. When this self-oxidation and reduction reaction takes place, a mixture of an alkanol and a metallic salt of alkanoic acid is obtained or are obtained as our product. Now we're going to look at the reaction on the board. Here I have this compound. This is methanol, 2 molecules of them. We use concentrated sodium hydroxide here as our alkali. This is 50% of this, so let me indicate it. Okay, 50% sodium hydroxide. Is that okay? Now, you notice that the methanol we used here, okay, the compound we are using here, does not contain any alpha hydrogen. Therefore, during the self-oxidation and reduction process in the presence of this concentrated sodium hydroxide, what is going to happen? Once again, I'm going to show you the mechanism of the reaction, just a brief look at what happens. We have our methanol. There are 2 molecules of them, so we have hydrogen linked to carbon. The carbon is double bonded to oxygen, and then we have another hydrogen. This is methanol. Now it's going to undergo self-oxidation and reduction reaction. So we have another methanol here, all right? And of course, don't forget, we have our sodium hydroxide. This sodium hydroxide is of great use in this case. So let us watch how the reaction proceeds. Here, one of these carbonyl compound is going to release the hydrogen attached to it. Of course, you have this hydrogen attached to a carbon of the functional group. So there is going to be a bond cleavage here, so that this becomes positively charged, and then of course we have negative. That is positive and negative. Is that okay? Then going to that of sodium hydroxide, there's going to be a bond cleavage here. So we have positive and we have what? Negative. Now watch. These 2 hydrogens will attack this carbonyl compound here. Will attack this methanol. These 2 hydrogens. They will attack this methanol. When they attack the methanol, what is going to happen? Once again, the carbon that is bonded to this oxygen being attacked, the double bond will break. And so this is what we expect to get. This is going to give us this compound, right? Half hydrogen. Then the double bond will break to single bond. This is our follow-com hydrogen here, 2 of them, okay? This is our oxygen. So you see how the double bond has been broken by these 2 hydrogens. Then one of the hydrogen will attach itself to this oxygen, just like nucleophilic attack, okay? And then the second hydrogen will attach itself here. And this is our methanol. This is simply CH3OH, methanol, which is an alkanol. We are not done. Coming to this part, what is going to happen? Remember, you have CO and H. Now, it's going to react with this sodium. Is that okay? It's going to react with this sodium oxide here, and of course, we are going to get our C. We have hydrogen there, attached to this carbon. And then, of course, this is O. And we have this oxygen and sodium here, so something like this. Okay? And this is sodium metanoate. Sodium what? Metanoate. It actually is sodium salt of alkanoic acid. These 2 products are our interest in this Cannizzaro reaction. So I'm going to write the product straight on. From here, we're going to get methanol, CH3, then OH, plus, of course, a sodium salt of an alkanoic acid there, which is HCOONA. Alright? And this is the compound we obtained from this Cannizzaro reaction. Remember, what happens is this. There is going to be a self-oxidation and reduction process. by the carbonyl compound, which must not have any alpha hydrogen. And then we have a mixture of an alkanol and a metallic salt of an alkanoic acid. We shall conclude the reactions of carbonyl compounds by looking at benzoin reaction of carbonyl compounds. The 15 in 6 major reactions of carbonyl compounds. Wow, it feels quite good to now come to the concluding reaction of carbonyl compounds of interest, which I'd like to teach you. We are going to treat benzoin condensation. This is another reaction of carbonyl compound. What happens in this reaction? Phenylmethanol is refluxed with aqueous ethanolic solution of potassium cyanide. When this refluxing takes place, the phenylmethanol condenses to give us the product 2-hydroxyl 1,2-diphenylethanol. This compound 2-hydroxyl 1,2-diphenylethanol is what we call benzoin. And of course, the reaction generally is known as benzoin condensation. We're going to look at the chemical reaction written, so you watch as I explain that and show it on the board, alright? In the formation of 2-hydroxyl 1,2-diphenylethanol from the condensation of phenylmethanol. Alright, so this is phenylmethanol. 2 molecules of it. What happens to give us 2-hydroxyl 1,2-diphenylethanol is much similar to the pathway that was taken when dealing with aldol condensation in the formation of aldols and ketones. Okay, so I'm going to quickly show you on the board here, alright, on how the product forms. We have our phenylmethanol, C6H5, phenyl, and then of course methanol. I'm going to expand this functional group part. Okay, this is phenylmethanol. It is as if the hydrogen in methanol is replaced with a phenyl group. Okay, remember methanol is HCHO. So that H is replaced with what? C6H5, phenyl. So you have phenylmethanol. Now it's going to condense with another phenylmethanol. So we have this. And now I'm going to show you what happens, okay? Let us assume that this phenylmethanol, the phenylmethanol releases this hydrogen. Is that okay? So we have something like hydrogen positive. And so this carbon, becomes a negative carbon. There, of course, this oxygen is going to remain there. Now we have 2 species here. This C6H5CO is acting as our nucleophile. It's acting as our what? Nucleophile. Then we have this hydrogen. They will attack here. Now, of course, when they attack, this is what is going to happen. This double bond will be broken. So you watch as I show that. This is going to be C6H5, then carbon. We have this carbon. This double bond will be broken to 2 single bonds. Let me indicate my follow-come hydrogen here. Then, of course, this oxygen. Is that okay? Now, this species that broke this double bond will now attach themselves to this carbon of the functional group. So look at what happens here now. The hydrogen will attach itself to this oxygen. I'm using blue marker to show that, giving us our hydroxyl. Then, of course, you have this C6H5C double bonded towards oxygen. Now, this is how the thing attaches. This carbon will attach itself to this carbon. Okay? With the doubly bonded oxygen. Then we now have our phenyl, C6H5. So this is our 2-hydroxyl. Because if you look at this compound, okay, it's an alkanol. It's an alkanol. This is the carbon of the functional group. So counting from here, you have 1, 2. On the second carbon atom, you have your hydroxyl. You have your what? Hydroxyl, making it 2-hydroxyl. Then you now have 1, 2. Because on the first carbon atom, you have this phenyl. On the second carbon atom, you still have this phenyl, making it 1,2-diphenylethanol. Let me write the product here. We go. I'm going to write the product without looking at this so that you see that you can actually write it out without bothering yourself with this breakups and showing you the full reaction, what happens to give you that product. So I'll just focus here and write the product. Is that okay? So you can find out how to do that. Let's go. We have our C6H5. Now this is the carbon of the functional group, this. And that is where the reaction will center. So we have this carbon. Remember, this oxygen that is bonded to it doubly will now break into single bond. This is the follow come hydrogen. Then of course we have this oxygen. Now this is the second single bond. I'm going to use red shade of marker to now show what enters. That's the second phenyl methanol group that will now enter. Remember that second phenyl methanol will release one of the hydrogen on the carbon of the functional group. That hydrogen will attach itself to this oxygen. Is that okay? And then you now have your CO and phenyl. So this gives us carbon, doubly bonded to oxygen. Then to read, we have our phenyl attached, C6H5. So this is the compound that we obtain. And the name of the compound, like I said, is 2-hydroxyl, 1,2. 2-hydroxyl, then 1,2-diphenyl ethanol. Let me write that. And of course, that is the benzoin condensation. Like we said, this compound is known as benzoin. With this, we've come to the end of the preparation and properties of carbonyl compounds. Watch the video lessons again and again. If you have a question, you always remember, you can send your question across to us and you get your response. In our next class, we're going to treat preparations and properties of alkanoic acid.